show that the series, the sum from n equals 1 to infinity, 1 over n plus 1, is convergent. And find its sum. This is definitely not a geometric series. If it was, I would have n only in the exponent. Here, I don't have that situation going on, so this is not a geometric series. So we can't use our nice information about geometric series here. Remember, one way that we tell if a series converges or diverges, the main way, is through looking at partial sums. So let's start looking at partial sums here. So if I want to write S sub n, remember that means I add up the first n terms. So I'm looking at 1 over 1 times 2 plus 1 over 2 times 3. So I plug in n equals 1, n equals 2, plus 1 over n plus 1. So you have a whole bunch of fractions you're looking at adding together. 1/2 plus 1/6 plus 1/12, right? One of the nice things, because we want to take the limit of S sub n, is that we want formula for S sub n. But I'm not seeing how to add these things together and get a nice formula. So what I'm going to do is I'm going to backtrack to our terms here, this in this series here, 1 over n plus 1. So I'm using n for S sub n, so I'm going to switch to using I now, so I don't get confused. 1 over I plus 1. This should remind you of something. If I replace this with x, these were functions that we integrated. I have a polynomial over polynomial. Do you remember how we integrated rational functions? We used partial fractions. So maybe that'll help us here. If I think about this here with partial fractions. So what are the fractions that I would have? A over x, Yeah, so I'm going to repeat what I did with x's, but now I'm going to do it with i's, because that's what I'm working with in my situation. 1 over I plus 1. So a over I and a b over I plus 1. Okay. And now we want to solve for a and b. So what did we do before to solve for a and b? Multiply. By this denominator, I plus 1, you multiply on both sides. So you'll get 1 equals a, I plus 1, plus b, I. And now we need to select values for I to solve for a and b. So what should I pick for I?
Have it equals 0 to solve for a.
So if I plug in 0 for I, I'll get 1 equals a. What other value can I pick? -1. So let I equal -1. And then 1 equals negative b. So this tells me b equals -1. Now the one thing that might be a little bit confusing is I'm allowing I to be negative numbers, but that's okay. I'm just using that to solve for the coefficients. So what I've done now is I've replaced 1 over I plus 1 with 1 over I plus negative 1 over I plus 1. Okay? So let's plug this into our series and see what it's going to tell us. So I'm looking at the sum from I equals 1 to infinity, 1 over I plus 1. I'm now going to replace that with these fractions. Okay? And then from here, let's start looking at our partial sums. So S sub n is what I'm using for my partial sum. So start by plugging in 1 into these two fractions. What am I going to get if I plug in 1? 1 minus a half, And then what? Plug in I equals 2. 1/2 minus 1/3. Let's look for a second real quick. Notice there's a minus 1/2 and a plus 1/2. So when I add them together, they're going to cancel, right? So let me go ahead and mark through those so I know that they cancel. Let's plug in I equals 3 now. What do I get? 1. Look at that minus 1/3 and the positive 1/3. When I add them together, I get 0. So they're going to cancel with each other.
It's approaching 1, wouldn't it? Because like the one that gets canceled out and you're always getting a smaller number.
Yeah, exactly. You've got the right idea. So let's show that though with a limit here. So what you're telling me is that, so I keep going until the last one I plug in is going to be this n value. All right, so let's plug in n. So this 1 over n got canceled with the one from before, right? With the term from before. So I'm just left with the minus 1 over n plus 1. So it looks like I now have a formula for S sub n. It's 1 minus 1 over n plus 1. Okay? And we want to take the limit of this as n goes to infinity. 1 minus 1 over n plus 1. What's that limit going to be? 1. So we just showed that the sequence of partial sums converges. So the original series converges, and we've already found its sum right here. It's 1. Okay, so let me sum up all that. The sum from n equals 1 to infinity, 1 over n plus 1 converges, and its sum is equal to 1. Okay. This kind of series is called something special. It's called telescoping. Anytime that you have terms that are canceling with previous terms in the partial sums, it's called telescoping. Okay. Do you have questions on that example?
Yeah. Why did you change that to I?
Because I'm reserving n now for the partial sums, so it's confusing if I use n in two places.
Oh, okay.
Yeah. If I wasn't using partial sums, you could still keep the n there. Yeah. Other questions? Yeah.
We shouldn't use x because we might confuse it for a function.
I mean, you could, if you're in the partial fractions process, you could use x if you want. But you can also just use I and not change it to x if you want. Because you're usually plugging in whole values for x anyways, a lot of the times when you're doing partial fractions. We saw that we would plug in a whole number. Like here, I plugged in 0 and -1, right? So it's okay to use I instead of x.